So today we're going to finish off our discussion of resonance. We're going to practice that a little bit. And then we're going to move into acids and bases in the context of organic chemistry. So what this does is this starts to look at our ability to take what we've been learning about bonding and how we take molecular representation and use that to look at different structures to predict basically stability. So this is reaching all the way back to acids and bases and general concepts from the first couple lectures. It reaches back to equilibria, talking about if some side of an equilibrium is more stable, the equilibrium will move towards that. Making those general statements, one side, let's say the products are more stable. Think back, what does that mean about delta G naught? If I make the statement that in some equilibrium, products are more stable, what do you know about delta G naught as a result of that statement? Plus or minus? Minus. What do you know about K for something where we say the products are more stable? Capital K will be what? Bigger than 1, less than 1? Which is it? Bigger than 1, because products over reactants is your expression of K. So these are the basic things we've been doing qualitatively. It's this interconversion between these conversations or these sort of terminology that we're going to be drawing on now. So where we left off last time, we'd introduced this concept of resonance. We had 3 main fraternities we want to look for resonance. What were they again? Give me one. Pi sigma pi. What else? Pi sigma lone pair. Last one. Pi sigma charge. And remember, hybridization, or having the stabilization because of resonance, number one, it changes things like bond lengths, right? Instead of what would have been a single bond, it looks kind of like a not quite double. It changes the distance between atoms. It changes stability. It changes where electrons will be. It changes where charge can be spread out. It also changes hybridization. So if you go through this one here, label each of these one at a time. A, B, C, D, E. Look at the nitrogen. Look at the lone pair of nitrogen. What is the hybridization? So starting on A. What's the hybridization of that lone pair? sp2, sp3, or sp? Well, okay, true. Sorry, let me step back. The hybridization of the nitrogen, yes. The hybridization of nitrogen is what? That's sp2. The lone pair is in what orbital? Where are we holding it? Where does it reside? It is in which type of orbital? The p orbital, right. The lone pair is in the p orbital because it is free for delocalization, it is part of a resonance structure, it is somehow involved in creating a resonance hybrid. So that nitrogen is sp2. Even though the current sort of single bond structure you see here, this is only one resonance representation. It is not the full true molecule, it's just one snapshot that you can arrange these electrons on. Okay, next one, B. What is the hybridization of nitrogen? What orbital is that lone pair in? Nitrogen is, yeah, this is sp3. Lone pair is in what orbital? Yeah, it's in an sp3 hybrid orbital. Just like all the other sigma bonds on that center. The bond between the nitrogen and carbon is formed because of a sigma bond involving the sp3 orbital on nitrogen. The lone pair is being held in an sp3 orbital. So the geometry of this nitrogen is what? Planar, linear, trigonal, well, tetrahedral, right? It's based on that kind of tetrahedral shape. It's like it was a carbon. Okay, what about this nitrogen? What's the hybridization of that nitrogen? Anybody say sp2? That's right, it's sp3. Why? No resonance. We have a pi bond, we have a sigma bond, but you have this other sigma bond spacing. This is also an sp3 center. Because of that, I can't draw a resonance structure. If I was trying to promote that electron down to make it interact with that other pi bond, I've got this sp3 carbon in the way. I would have to break sigma bonds to create structures that are allowed by orbitals. So that's not allowed. What about D? This is what? sp2, sp3? Yeah, this is sp2 again. Lone pair is in what orbital in that case? The lone pair is in, well, it's held in the p orbital. It's reserved in the p orbital. Why we say that? Lone pair gets held in a p orbital so that it can make a pi bond. That's why the hybridization on nitrogen is at this lower sp2 state. Basically, if this lone pair in any sort of resonance contributor, you form a pi bond with it, what you're saying is, I would take this lone pair, let me draw that one out this way. What we're saying is, if I had indole like this, one valid resonance structure would be, take this lone pair, promote it down, take this pi bond, and park it over there. I will create a resonance structure where I now have a double bond between nitrogen and carbon, and I have a lone pair chilling out on this center. As a result, positive charge, negative charge. So what I'm saying is, this lone pair right here, at some point in time, becomes part of a pi bond. Thus, it has to be held, reserved in a p orbital, so I can make a pi bond at some point in time. If we had an oxygen there, two lone pairs, how might you divide this up? If we had the same oxygen that had, let me draw it this way. Oxygen, same thing. Two lone pairs where I have pi bonds on either side. In a similar way, I can promote this down. I can promote that up. It has that same pi sigma lone pair type structure. So I can create something that looks very similar. Double bond this way, lone pair out on carbon, positive charge on oxygen, negative charge out here, where one of those lone pairs is always just chilling out on that oxygen. We have two lone pairs there. For those two lone pairs, what orbital would you say this guy is in? That's in which orbital? Yeah, it's in a p orbital because it eventually becomes part of a pi bond. This one here is in which orbital? Do I ever need to use that one? I need one of them to be in a p orbital. I do not need both of them. This guy here will be chilling out in a normal sp2 hybrid orbital. What we're saying is, although there are two pairs of electrons, two lone pairs available, one of them needs to be available for resonance. The other one is going to stick out from the ring almost like it was a normal sigma bond. So in the case if we have multiples, the same rule applies. What you're really saying is if it has to be involved in resonance, that's where it must be reserved in a p orbital somewhere. Last one. That nitrogen is, altogether, sp2. Lone pair is in what orbital? P orbital, that's right. So we're just going through these and identifying cases where resonance is existing. Yes? Say that again?
Could you do two resonance structures at the same time with both lone pairs, creating one?
Back to the oxygen, you mean?
Yeah.
Okay, let's take that one up. So the question is, we've got two lone pairs. Is it possible that we could use either? What I mean is, I'm going to migrate this one down to form that resonance structure we drew. Like this. Lone pair, negative charge, positive charge. I can't take, there's no other valid structure. If I took this lone pair and tried to do something else with it, like that, what happens here if I did this? So let's actually, this is a really good question. First of all, what I was originally going to start on is, since most of the time, only one of the two will be needed because we're only going to have one of two pi bonds to that oxygen in any valid structure. So we're really saying that only one of them has to be P, one of them can be sp2. But let's take this one here. So far, the arrows I just drew here in green, does anything look wrong so far? Are we on track for something that looks bad right now? Is this flagging anybody as not a good thing? Okay, so far looks good. Let's draw the structure. All right. The sigma bonds don't change, right? So it's still a 5-membered ring, right? I did not touch this pi bond. I still have a lone pair over here that's negatively charged. Oxygen was positive, but we just took the other lone pair and I created a new pi bond here, right? I also took and I put another lone pair out here. What's that oxygen have to be for charge now, based on how I've drawn this? +2, okay. So first off, does this look bad? Not great, right? Because we've separated charges. Would you consider this to be a major contributor, just based on our rules? Not so much, but there's actually one more piece to this. This is not a resonance structure. What is the hybridization of this oxygen you see here? Oxygen with 2 pi bonds to it. What must that be? If that was correct, what must the hybridization be? sp, good. All right, so as we've drawn this, this here is sp, has to be 2 pi bonds. What's the geometry of an sp center? Okay, linear. What does that look like? Must be linear, right? So in addition to being, okay, we've just jacked a whole ton of charge into this, not great, that oxygen would have to be linear. That means that 1, 2, 3 atoms all have to be 180 degrees. If you get your model kit and you try to build this, you will be eating a bond in your eye. It will blow up. It is impossible to take a 5-membered ring, 6-membered ring, 7-membered rings, usually these ring structures like this, to put an sp hybridized atom in the middle to create it linear like that, creates such ring strain, the molecule would pop. Really what we're saying is, to make this structure, these 2 double bonds, we must create pi bonds, which means that has to be in a p orbital, which needs that side-on overlap. Geometrically, it's not possible here. Yes?
Oh. I was going to ask why specifically it doesn't work. Like, what makes it not a resonance structure? That it floats?
If you try to draw this, the geometry that would be forced to create those pi bonds, you would have to have 2 p orbitals that are doing nice side-on overlap. To create that geometry, it makes all of those atoms, these 3 here, have to be collinear for this to ever exist, to create that pi bond. Since geometry twists it, it can't make that structure, it's bent around that corner, there's no way to take those electrons and create 2 pi bonds to this center in this ring. Can't be a resonance structure. It's a similar thing as if you were drawing this out and saying, okay, I wish to push these electrons to the center. That would break hybridization, or it would break, I would have to actually eliminate a sigma bond in order to not go over 10 octet. Similar idea. Bonding would sort of implode on itself. That's it. Make sense? So at any point in time, the only valid resonance structures is something this would only involve one of the 2. Yes?
What if it was not cyclic and it was just aligned?
If it was not cyclic and aligned, you got a chance. That is true. If you had a linear structure where you don't have this sort of baked into it, now it could potentially form. Absolutely true. Yeah, this is force based on how the ring is. So yes, if it could bind itself off and straighten it out, definitely possible. Even in that case, though, is this a major contributor? No. Doubly charged, everything else, so it'll be a minor guy. Good stuff, though. All right. So we've covered through our resonance. These are our arrows to sort of move through it. Work through the problem set. We've given you a bunch of examples to practice moving these electrons, identifying structures. And as far as how you identify the resonance structures, the best practice is to walk through them. Look for those patterns, promote them according to valid movements of your 2 electrons, and look at what you form. Just like the exercise we did here, there's nothing wrong with, I will try this out. But interrogate the molecule you drew to see, does there something that violates your idea of stability, right? Usually if you run into something that you've never ever seen before, it could mean that you've gone down a dark path. It could be a very rare case, but those are also the ones easily. If you ever draw something out and you're like, could this exist? Take a picture with your cell phone, shoot it to me. I'm happy to walk you through it. What we're going to move to next is mechanism. And specifically, mechanism is now where we're breaking or making sigma bonds. We're making new bonding relationships. And we're going to start by practicing with acids and bases. These are the most simple reactions we can talk about because there's an exchange of protons, small centers. So remember from before, Bronsted acids were donors. Bronsted bases are acceptors. Every acid and base equilibria will have an acid base on one side and a conjugate acid and base on the other side. This is how they're connected between the two. Remember, the only difference between an acid and its conjugate base is the addition or subtraction of a proton as you move between this equilibria. So what this just really means is, for every acid and base equilibria, you can think about it as a concert of some acid and base on one side and its conjugate on the other. Since we're only moving a proton back and forth between the two sides, we could look at this and say, if I understood something about, let's say, the stability of the acid or the stability of the base, I could compare acid here versus acid here and ask the question, which is stronger? This is like a tug of war. Really what we're evaluating here is, on either side of this equilibria, which side is going to hold on to that proton better? In other words, a very stable acid here, what does that mean about this equilibria? If the acid HA was more stable than the acid BH+, which way should this equilibrium move? If I said this was more stable, equilibrium should move to the left. By identifying a component and saying that acid versus acid, if this is more stable, equilibrium will move towards the more stable species. Likewise, if I said HB+ was less stable, it'll move away from that species. So direction of the equilibria can be counted by looking at the species that are present and identifying stable structures. Now, in a guy like this, first thing we have to do is practice how do we use arrow notation to complete an equilibrium, or complete an acid-base set. Remember, for every acid and base, there's the movement of one proton. So I'm going to start off by saying I need to form a new bond. If you look at this, we're forming a new bond between the base and that hydrogen, and we must break a bond between the oxygen and the hydrogen. That's the atom that's moving between the two. New bond is being formed, and a bond is being broken. What that means is there must be a total of two arrows at least, right? We need to make a new bond, which means electrons are reaching out to create a sigma bond. That's 2 electrons. And we're breaking a bond. We're taking electrons that used to be in a bonding relationship, and we're moving them to be on an atom. So when we draw this as equilibria, you start on the base. We put our pen down where there is electrons, in this case the nitrogen. We take that lone pair, and we're going to form a bond with the hydrogen. The way you draw this, arrow will point towards the hydrogen. Now, by convention, this is okay. What you're inferring here is that these electrons will be part of a bonding relationship between hydrogen and nitrogen. What's not okay, this is acceptable. Usually what we're trying to do is show that a bond is being formed, so you usually stop forward with your arrow. What's most important is they must start on these electrons, and I would usually target this where the front end of those arrows are pointing here, into the void space where a bond will exist, not directly at the atom. That's not the end of the world, though. This is a little bit of bad penmanship if you decide to point at a hydrogen. What would be very poor, though, is if I were to draw out this base, lone pair, and my OH carboxylic acid. Please, please, please do not do any of these things. 1, that. Why is this wrong? We don't know. There's not enough information here. You're sort of saying electrons are moving from this area to that area, but you're not being explicit enough to say that they start here, it is this lone pair, and where is it going? What's wrong with that? If I'm pointing there, what does it look like those electrons are flowing into? Yeah, into oxygen. Why is it doing that? You have to be explicit in terms of where you start and where you go. So this is very bad penmanship, not specific enough. That would be error number 1. The other really, really common thing I see with acid-base reactions, oh, I'm doing an acid-base. This is my base. Here is my acid. Okay, great. That hydrogen needs to go right there. What's wrong with that notation? Remember, your arrow is talking about where electrons start and where they go, how you form new bonds. This is describing hydrogen went over there. That's the direction or movement of an atom. That's not what two electron arrow notation is for. This is basically saying electrons from the hydrogen are going into the nitrogen. The electrons are actually promoting there. This would be moving of a hydride, H minus, not H plus. It's not a pole in that direction. So that's another thing to watch for. Directions of arrow flow has to be from where they start, this is on lone pairs, or where they go to. All right, that's the first thing. So you start at the base, you move into this space between where the new bond is going to be formed. Am I done? What's wrong with just the arrows I've drawn here? What would the product of this reaction be if I just left it with that one green arrow? Hydrogen is bonded to two things, right? I've created a new bond between nitrogen and hydrogen. Hydrogen is a serial monogamist. If it's going to be bonded to something else or dating the nitrogen, it has to break up with the oxygen first. So you must have two electrons. Hydrogen is sitting there, long committed relationship with oxygen. The base comes along, this looks a lot better. Nitrogen will reach out, make its offering with, I've got these great electrons, why don't you come with me? Hydrogen says, that sounds great, see you later. Oxygen, I'm done.
I'm having trouble hearing you.
Wow. Every time. The point is, there must be, since you are rearranging two bonds, you're forming a new one, you're breaking this one, there must be two pairs of electrons moving. There are two arrows that represent this migration. What happened there? Oh. That's weird. Yeah, that's not too good. Okay. So, for this one, if this was the product that we've drawn, if this is what we're forming, I've identified here and I said that that hydrogen is my acidic proton, which means the thing holding that hydrogen is the acid. How does this look? What do I do next? What's the base, first of all, based on what I've drawn right here? Yeah, water's the base here. Does anybody recognize this species? That is what? H2SO4, that's what? Yeah, sulfuric acid. Is that one of our strong acids you guys remember? Yeah. What am I explaining here, though? H2SO4 plus water. What is this equilibrium we're talking about? Do you remember this? An acid giving its proton to water. It was a special name for the equilibria. This is the Ka. This is the Ka equilibrium. So, if we've identified that this is the proton we're going to be donating, that means this is my acid. That makes this my base. All right, now I know who the two players are. You've got two choices. All acid-base reactions, if we're drawing them by arrows, the arrows start on the base, they reach out to the proton, they break the bond between the hydrogen and the conjugate base, the rest of the molecule. So you can start by drawing those. The second thing you can do, too, is you can complete this equilibria. You know, if this was the Ka equilibria, H2O is going to form what? What's on the other side of the Ka equilibria? H2O becomes, right, we know we're going to make H3O plus. That's going to be one of my products. And also, I'm going to have my conjugate base. That's all of the other stuff here minus that proton. So it's sulfur, oxygen, oxygen, OH, and a negative charge on this oxygen. Remember, your charges must balance. For any acid-base reaction or any of these, we're keeping track of where electrons went. Oxygen ends up plus, sulfur ends up, or the oxygen on sulfur ends up negative. Net charge is the same on both sides. We're counting all the electrons and atoms. So to complete this equilibria, or the acid-base notation, I would start by saying, okay, one of the lone pairs on oxygen is going to be my base. It will form a new bond between oxygen and hydrogen, and this must donate electrons back to oxygen. I have to break the bond between HA, the acidic side, and I need to form a bond between lone pair and my base, or my acid, yes? You don't necessarily have to. It's a good practice if you do. But basically what we're saying in the end is a bond must exist between that oxygen and this hydrogen. You don't explicitly have to put the lone pair back in. I will understand what you mean there. What it does mean, though, is in cases like this, here we've explicitly expanded this OH. The other way you can draw this would be sulfur, double bond oxygen, OH. OH, double bond oxygen, right? What if we wanted to compress or not show the sigma bond between oxygen and hydrogen? In this notation, it gets a little bit hard to draw your arrows. If I had my water here, drawn out this way, if I wanted to get my lone pair, grab this hydrogen, this gets a little tight. Again, not totally wrong, but it gets a little bit harder to mark because I'm not 100% sure. Do you mean oxygen is just doing this weird Ferris wheel where it spits out electrons and then back? Or do you mean you're breaking this bond? When you're drawing these as good practice, be explicit. I would expand this center to specifically show oxygen, hydrogen, and that way there's no ambiguity. You are picking off this hydrogen, you are breaking this oxygen, right? You're being very specific that you show where those electrons are going. Good penmanship, good practice here helps you. If you're clear about what you're saying, it's easier for us to mark it. Okay. So, numerically, we have ways of talking about the stability of different acids and bases. One of the common ones you guys are used to now is pKa. What did we say about the acid that has a low pKa? Stronger or weaker? The lower the pKa, 0 or negative, it gets much stronger, right? A bigger pKa number, weaker. So based on this, given this equilibria, we have two pKa's. Here's the acid on the left-hand side, and its conjugate acid on the right-hand side. And we've given two pKa values. Which one's the stronger acid, HA or BH+? HA. Which way does this equilibrium move then? Right. This guy here is stronger. It will push harder. It must move to the right from the left. The stronger acid is the one that's going to push harder to donate this out. So saying something about HA is a stronger acid, you're talking about this little tug of war between two acids. The equilibrium favors moving away from the strong species, moving towards the weak species. That's like saying the things that lie on the product side here, yes, they're weaker, they're also more stable. Those are the same things we're going through. So what do you think is the better base, given this equilibria? Is it B or A minus? Which is the stronger base? Stronger base. Which way did the equilibrium move? The stronger acid is on the right-hand side. Guess what? The stronger base? Also on the right. The side of the equilibrium you move away from, conservatively, what we're saying is, we've got these two species as a relative structure. If this is my strong acid, then the other species here must be my stronger base. In this specific case, and this is where I'm not talking about, oh, is B a strong base, like compared to hydroxide or compared to T-butyllithium or something? No. I'm saying in an equilibrium specifically here, I'm only ranking base B versus A minus. I'm ranking HA versus HB. Since the pKa tells me HA is a stronger acid, its conjugate base will be very weak. If HB is a weaker acid, B must be a stronger base. That's the other way we can sort of view these. This is also starting to talk about terminology and relative structures. The thing to remember, though, is if the equilibrium moves away from something, it's moving away from both strong species, both the strong acid and strong base. If we have the strongs on opposite sides, then somehow strong acid is pushing hard, but strong base is coming up from the end. That would be really weird. In the end, this is an expression of why this happens. It's not just because HA is the stronger acid. HA in the context or in the presence of B produces that sort of geometry. So as long as we can identify the strong acid, we know in some comparative acid-base equilibria, that side of the equilibrium will contain the strong base as well. It moves away from those two species. Okay? So, what about now? Who's the strong acid? Who's the strong base? Which way does this equilibrium lie? Right or left? It's which way? One more time. I want everybody to yell it out in concert. It is? Left. Because why? This is a stronger acid now. Stronger acid, which means A minus is the stronger base. The equilibrium must move away from that because HA is the weaker acid given this system. So it moves to the left. What is the more reactive or better base? Again, in this case, it'll be A minus. You're moving away from those two species. So having numerical values for a head-to-head comparison between two acid species allows us to pick which way this should go. But again, most important, we're talking about a pair where you notice here, we're ranking this acid versus its conjugate acid in this one-to-one or binary type comparison. We're not making general statements about in the context of the world or in context of sulfuric acid. We're saying given only two abilities or two species, which way does it go? So based on this, what's the magnitude of the equilibrium constant? Same species. Which way does it go? Right or left? We said it's going left. So what's K? So everybody all together, A, B, C, D, or E, it is? E. That's right. It's going to be less than 1 because the equilibrium is starting material favored. Remember, that is the concept of also how we've drawn it. What would this change if I wrote it the other way? If I wrote this A minus plus HB positive to form HAB, what would happen to the value for K? I'm flipping the whole thing around. Value for K will now be greater than 1. Perspective matters. As drawn here, we are to the favor of the left, which means K is less than 1. If I was to invert these two, turn it all the way around, now it's a product favored equilibria, K will have to be greater than 1. So what this just means is we have a way, if I'm trying to decide between two acids, who the stronger acid is. If I set up a comparative acid-base conjugate pair like this, I can use information about this equilibrium, its position, to come up with a ranking of who's stronger and who's weaker. So let's take these guys. Look at the relative pKa's. So water, do you already know that second molecule, the C-triple-C, 2 hydrogens, you know the name of it? What's that? Ethine, yeah, or acetylene is the other common name for it too. It's a fuel that we use for very hot fires for welding. So we have water and acetylene. And we've got a hydrogen here, and let's say a hydrogen here. The pKa of water, 15.7. pKa of that hydrogen I've circled on acetylene is 25. Who's the stronger acid with that information? Yeah, water's going to win. Water should be a stronger acid between these two. Fine. So what we can do, though, is if I'm representing this as this head-to-head equilibrium, step 1, we draw the equilibrium out, and I'm going to put both guys in their respective corner, either side of an equilibrium. If I'm trying to evaluate the strength of these two species, what I do is I put one acid on one side of the equilibrium, one acid on the other side of the equilibrium, and what I'm going to say is, okay, in this relationship where the conjugate acid or base was to be part of it, I'm going to put them in their own little corners. Now, to complete the equilibrium, what is the conjugate base of water? If water acts like an acid, what does it form? What's it? OH minus, hydroxide, right? Okay, what about if acetylene was to act like an acid? Its conjugate base would be what? Negative charge where? If the hydrogen I've drawn is the one that's acting like the acid, it's going to be, you're losing this, so it has to be something that looks like, oh, triple carbon, lone pair, minus, right? That CH bond, if it were to lose that proton, just the same way as the OH bond loses the proton, it leaves behind a lone pair and a negative charge. So what we now have is the acid on this side and its base that we're comparing. over here, this pair, this is my conjugate base and my conjugate acid from this particular respective point. So what we did is we took two acids we're trying to compare, put them on either side of the equilibria, and then we fill in the equilibria with the respective conjugate bases for each. Water's conjugate base is hydroxide. Acetylene's conjugate base is the species minus the proton I'm trying to evaluate. The only proton is that carbon-hydrogen. I'm ripping that off. So this is where things get weird. pK of 25, that does not sound like a very good acid. And you're right, the equilibrium here, water is going to be the stronger acid. So in this equilibrium, the one I've drawn here, comparing just these two, right or left, what is more stable? Yeah, this is a stronger acid. We expect it to move this way. This is my strong species. What does that mean about this base? Stronger or weaker? Stronger. So now putting verbs to this, or language. What this diagram is teaching us, acid is a stronger acid, water is a stronger acid than acetylene. Acetylide, the conjugate base of acetylene, is a stronger base than hydroxide. Does this mean if I gave you acetylene, this guy over here on the product side, and I gave you hydroxide, this guy, can I deprotonate acetylene with hydroxide? Can I go to this side of the equilibrium? Is that favored? No. Water and acetylide, these are my strong species, and we said it moves towards left to right. That means if I started on this side, a tiny bit might go over here, but that equilibrium heavily, heavily favors the product. The statement I get from this, the prediction is, if I were to take acetylene, this guy over here is a product, and I mixed it with hydroxide, this guy, these are my weak species. The weak species are not going to do a very good job of reforming this side of the equilibrium. What I'm saying is hydroxide is not a strong enough base for me to do this chemistry. I would expect that if that happened, it would snap back very quickly. Forming acetylide and water would just snap back to form my two products. The equilibrium lies so far in favor of this thing, these are not a good combination to form those species. I would have to find some other combination. This is not a good enough base to do this. So prediction of strength here allows us to predict what's happening in this equilibrium. So drawn out neatly, we place the acid and both acids on either side of the equilibrium. We complete that equilibrium with their conjugate base pairs, filling in the different components. Based on the numbers we have available, we predict that the equilibrium should move from right to left, or sorry, left to right, excuse me, yes?
If the equilibrium so much to the right, would that just become an irreversible reaction?
So that's where you can start looking at the numerics. pK of 15 versus pK of 25. What do you know in the pK scale? For every value of 1, that's something like, remember, it's log 10. That's times 10, like 1 to the power of, or 10 to the power of x, right? That's 10 to the power of 10. That is a massive difference in this equilibrium. So yeah, this would almost be completely irreversible. If you put water and acetylide together, there is no going back, just because the relative difference of the two pKs are involved. The same thing applies, though. If this was 15 and this happened to be 16, still stronger. It's just a little bit closer to balance. Yep. So this formalism is something we're going to practice repeatedly now. Given any two acids, you should be able to look at these things and the rules based on the relative pKa's and come up with intuition that says which side of the equilibrium do we expect to be favored, okay? So if you are not given pKa information, though, this is where it gets a little bit trickier. This is where we need acids and bases and the relative stability to do this. So who remembers the matrix? There's just a recent, oh, wow, every year this gets worse. There was a new matrix recently. The most famous quote, so you're going to tell me you can dodge bullets? No, when you're ready, you're going to be able to pick pKa's and acidity without having to go back to formal tables. So what we're going to do now is teach you to be Neo. The position of the equilibrium, based on what we've talked about, is based on stability. So fundamentally, we've got to go back to things that we've talked about, bonding geometry, what makes a molecule more stable, and be able to predict which side of the equilibrium lies. In general, like we said, stronger things, those are higher energy, equilibriums move away from them. Weaker things, those are the stable species, equilibriums will move towards them. So our job now is to predict relative stability of these systems. Remember, this is what this looks like. When we say more stable, we're saying the delta G naught is negative, or moving towards that one is lower in energy relative to this system goes. We're not going to be talking so much necessarily about this dip, the extent of reaction. We're just saying preferentially, is it going to favor the right or the left? And it's about looking at the stability of those systems as we do this. So we're going to focus, though, and we're only going to look at things that fall into these two categories. We're going to focus only on cases where a charged species exists on opposite sides of the equilibrium. So what I mean is, if you took a system in the top where you have a neutral base and a charged acid to make a different charged acid at a neutral base, or a negative base, neutral acid, makes a different neutral acid and another negative base. The reason we're going to do this is it helps us to focus, because really what we're doing is saying, if you focus on these charged species, we can ask the question, of those two charged species, which is more stable? We're talking in general. Remember, neutral things in general are relatively stable. Charged systems are generally less stable. So the rules we're going to teach you is to find the negatively charged species or the positively charged species and rank them. So in a case like the top one, we'd be asking which side is happier being positively charged? Or in the second one, which of these two is happier being negatively charged? So the kind of system we're not going to consider would be something like HA plus base in equilibrium to make A minus and HB plus. The reason why we're not going to consider this one is because all of the charged species are on one side. Okay, so we're just taking this off the table right now. These are better done where if we had, let's say, sulfuric acid, neutral, and water. So sulfuric acid and water, we know that's a strong acid-base equilibrium. We know that will be promoted through this. So intuition in that context, you do need to remember, but for the point of prediction, what we're going to focus on is only the first two. Cases where there's charges only in one of the two components, okay? So what this does is it narrows the focus of all the different systems we can look at. There are 4 rules you must know. And ideally what we'll do is we're going to set up systems where only one of these 4 rules is the major deciding factor. So your job is, first of all, know the rule, know how to apply it, and how it helps you predict. But ideally, we'll set up a system where only electronegativity is deciding, or only resonance is deciding. The reason I state that now is because depending on how you look at certain molecules, you could look at this and say, oh, I think this is an inductive effect. I think this is polarization. Or you think multiple are happening. But the big tell I'm telling you right now, we will always set up problems such that one and only one is the deciding factor. No matter how tricky it might look, there's always a clear one. We will try to stay completely away from cases where, oh, there's these 3 acting on this side, but then there's this one. Like, we try to make it much cleaner than that. So if it really, really starts to bug you that, wait a minute, there's multiple things going on, stop, take a breath, look deeper. You're probably overthinking it. This is also not a ranked order. We're not saying that electronegativity is better than resonance. We're telling you these are 4 cases, and in all times, one of these 4 will apply. All right. Number 1, electronegativity. Electronegativity is talking about the happiness of a negatively charged species. In general, if a negative charge resides on a very electronegative atom, that's a good thing. Compared to negative charge on an electropositive atom, it's a bad thing. The reciprocal also exists too. If we put a positive charge on a very electronegative atom, that's bad. So the thing you have to watch here, this is our periodic table. Remember the trend of the periodic table? Thing to grind into your head, fluorine is king. Fluorine is the most electronegative atom because it sits in that top quarter, left to right and up to that corner. Oxygen is your next most electronegative. These are the ones you're focusing on, and if you have the ability to put a negative charge on one of these centers, that's great. The most important thing with electronegativity, though, is this point here. Sorry. It's the atom to attract it from within a covalent bond. That's the electronegativity trend. How this applies is that we are looking at, within the same row, ranking negative charge on atoms. What I mean is, what is the stability of different electronegative atoms as we move left to right? Carbon, nitrogen, oxygen, fluorine, not fluorine, chlorine, bromine, iodine. This is only really a trend that follows as we move across the periodic table within the same row. So we're ranking how does a negative charge favor as we move in that sort of table. Generally speaking, negative charges are more stable on more electronegative atoms. In other words, if we had carbon minus as compared to oxygen minus wins. That will be a more stable one. Likewise, the opposite is true. Oxygen plus is not as good as carbon plus for the same reason. Electronegative atoms are not happy there. So looking at these two, A or B, which is more stable? Everybody together, it's A. Why? Yeah, you're checking oxygen versus nitrogen. This is more electronegative. If it's more electronegative, it should be more stable. Most important thing, though, when you're using electronegativity, the atom we're checking has to be the atom that's holding the charge. For example, what if I drew, oh, no, it's not going to work. Let me draw that OMe, nitrogen, lone pair minus, versus and the thing I'm trying to highlight, here I've got an oxygen, here I've got a carbon. What atom in both the two new structures I drew, which atom is holding the charge? Carbon, nitrogen, oxygen, fluorine, bromine. Which atom is charged negative? So which atom holding the charge is more electronegative? They're the same. I cannot use electronegativity to decide which of these two is more stable. Why? Nitrogen is negative, nitrogen is negative. They have the same electronegativity. This is not how you differentiate these two. This is something else. We'll have to go to one of the other categories. Yes, this molecule has an oxygen that is electronegative, but that's never holding the charge in this case, so it's not the reason we say it's more or less stable, okay? Electronegativity is specifically about an atom holding onto the charge. It has to be the formally charged system. So in the top one, oxygen versus nitrogen, that's easy. So which of these would you think is the stronger base? Which of these, if we were to rank these in that thing, we said who's more stable, A or B? More stable is A. So if I had an equilibrium where these were on opposite sides of the equilibrium, which way will it move towards? Move towards A or move towards B? Towards A. So which is the stronger base? The thing you moved away from, B. B is a stronger base than A because A is a more stable ion compared to B. So the stronger base here will be the thing you are moving away from, the less stable species in this point. So this is where this nomenclature is important because it allows us to identify these. The last thing I want to talk about in terms of electronegativity. We finally, like the most way we apply this will be carbon, nitrogen, oxygen, or silicon, phosphorus, sulfur, right? Left and right in a row. However, hybridization matters. Hybridization, if we had an element that was sp3 hybridized, we say that's less electronegative compared to sp2, compared to sp. What this just means is if I had a carbon that was sp3 subsidized, negatively charged, versus a carbon that was sp hybridized, this guy is more electronegative because it is an sp subsidized charge. They're both carbon, but since the hybridization is different, That's going to help us. Now, why might this happen? How could you rationalize this effect? Think about the size or shape of an sp3 hybrid orbital compared to the size or shape of an sp orbital. Yeah?
The density is more concentrated on the right.
That's it. If you look at this, an sp3 orbital is made up of 3 p orbitals and 1 s. S is concentrated at the center of the atom. So with those 3 p orbitals, it ends up being much more elongated. Think about it, it's 1/4 s orbital. The sp orbital is made up of 1 s and 1 p. The percent around that core atom is much larger. It's more s character. It's more localized around the atom itself. It's more dense. So as a result of that, if I had a negative charge that has to be an sp orbital, it's mostly held close to the atom center, electronegative. In sp3 center, it's more diffuse. It's reaching out because it has this longer projection. As a result, less electronegative. But again, it comes in cases like this. An sp hybridized carbon is more stable than an sp3 hybridized carbanion. Okay, guys, we will pick up on Monday with the other 3. Have a great weekend.